The broadcast is now starting. All attendees are in listen-only mode.
Sorry about that, folks. This is Steve Wright speaking. I had some administrative snafus there that I had to attend to. I hope everybody can hear me now. Today we're going to talk a little bit about the application of external device monitoring with the Siemens safety PLC. So I'll get right to it. The first thing to do when you start any safety program is to do a risk assessment, and part of that is the identification of the safety functions. I include this little chart here just as a way to sort of a form I use to make them as specific as possible. So in this case, we're going to talk about a single safety function described here. If the guard door opens, I want a motor to switch off, and it requires a number of tasks, but we'll sort of I won't go through all the elements of the risk assessment and the safety validation, and we'll talk about some of the specific uses here. This is a little snapshot of our hardware configuration. Some of these names for the inputs and outputs we'll see later when we go through some more of the code. But essentially what I'm doing is I have a guard door here that in the closed position, these two switches are normally closed, and the action of opening the door will drive those switches open. Those switches are connected to this fail-safe input module. Down below it, I use some acknowledgement, because what we'll see later, I'm going to configure these switches so that every time I open the door, I require a manual acknowledgement to restart the machine. And that's going to be noted by this blue light. It's going to be illuminated when I need that situation. Up here above, you see just some standard push buttons that I'm going to use for my design here. A blue button for acknowledgement and a start and a stop button. On the output side, I have a fail-safe output module that's going to drive my contactors to start and stop my motor. And then finally, the normally closed auxiliary contact in series from both these contactors. It's going to go to a standard interface module here to represent my external device monitoring. I'll move straight into the hardware configuration, first into the hardware configuration for the fail-safe input module. I've made some choices here. You can make other ones. First, by deselecting this top box for manual assignment of the F monitoring time means that I've chosen to accept the PLC default F monitoring time that's configured when you configure the safety CPU. F monitoring time is a watchdog timer to ensure that there's proper communication between the F CPU and this fail-safe input module. How you determine those F monitoring times, Siemens has a spreadsheet that's available on the support site called S7FCOTIB.XLS, and I'll have a link to that at the end here, which is it's actually a very complicated spreadsheet, but it's important if you have a complicated system that may require an adjustment of this default F monitoring time. The F destination address is the address of this particular I/O module, and each fail-safe I/O module has a unique F destination address within a project. You can change these numbers, but the numbers need to be unique within a project. I've chosen here that if my behavior after a channel fault is should this channel experience a fault, I'm going to passivate the entire module. The other choice is passivate the individual channels. Passivating the entire module requires a little less time, so it may again help your F monitoring time. And finally, I can manually assign numbers to the data blocks that are automatically generated when the hardware configuration is compiled. By selecting this box, I've chosen to accept the default numbering scheme but you can adjust your numbering scheme. Lots of people do that to put certain data blocks in particular places. The second screen for configuration of this input module, I'm going to define this module that I'm going to use a short circuit test on channels that are supplied from an internal sensor supply. What that means is with an internal sensor supply is power to these input devices comes from the module, and when the short circuit test is enabled, the module turns the power to the input device off for a short period of time, a little less than this input delay you can configure here, just testing for short circuits to the input device. You saw that I have two switches on that guard door. I'm going to configure them for 1 out of 2 evaluation, which means that I assign the 2 input switches to specifically paired input points on the module. They are equivalent interconnections. Those 2 channels must be in the same state for at least for the if they were in different states in excess of this discrepancy time, that would cause a channel fault. I've selected a longer discrepancy time, 500 milliseconds here, just because those 2 switches you saw are independent mechanical switches that may be difficult to completely synchronize, but you can adjust that time also. And then if I see a discrepancy, what I'm going to do is I'm going to have that input go to 0. It's possible for you also to supply the last valid state, which would be the state of that input the last time it was cycled and there was a valid signal there. But generally and most commonly we supply value 0. If I get a discrepancy error, I've said I don't need to test it, which means let's say if I were to get a discrepancy there and this were set to test signal necessary, that would mean I'd have to open and close the door just to get this input to go back on again. You notice that in my example I'm only using a single input channel, so the other channels are deactivated, which means they're not part of the I/O scan. We turn to the configuration for the fail-safe output module. Again, I've deselected the manual assignment. I'm going to accept the default F monitoring time. It has a unique address, and again I'm going to passivate the entire module. You can adjust these settings as you wish, but these are sort of the most commonly used ones, these settings I have here. Let's look at this. Again, I'm using a single fail-safe output channel, so I've activated only one channel. But I'm going to use I'm going to require the wire break diagnostics, which means that for it's a little more complicated than the short circuit test on an input module. What that means is one, that I have to have an actuator connected to this activated output, and there's a bit pattern test that can be done on fail-safe outputs, which means that the output is very rapidly cycled on and off. There's 2 parts of that. A dark test is about every 15 minutes when the I/O module is working correctly, this bit pattern test is executed. The dark test is done when the output signal is high, which means that the output is very rapidly cycled low. So it's actually the pulse that drives it low is going to be less than its readback time. Likewise, the other half of that bit pattern test, the light test, is when the output is supposed to be 0 I rapidly cycle it high for this term just to make sure that it's still operating correctly. You might have to adjust this readback time if the actuator you're driving with this output is more capacitive. And that's what it's checking. That's what the module is checking. I told it to go low, and it is in fact low. So that's kind of a real quick snapshot as to how you would configure these modules. In essence, for this example, I've selected some what I consider more common settings for the hardware configuration. So if we move to the PLC programming for a little example here, you'll see that I'm going to have my OB1 as always, which is just going to do my starting and stopping, and then I have created another function block that's called here. That's just going to be my HMI code or transfer of data. OB35, again, most commonly used cyclic interrupt for starting the safety program. You'll see I'm going to send some status to the safety program, and here's where I'm actually going to call my safety program. 100, my main safety program, it's going to contain a call to my reintegration routine and actually my logic I'm going to use for this example. DB200 is a fail-safe data block I've created to transmit some information to the standard program and also a little bit of use within the fail-safe program. So let me switch to the code here and we'll see what we can see. I'm looking here at OB1, and you'll see I've my first network here. I just have a simple start-stop circuit. Personally, I prefer not to use set and reset bits. So what I've done is I just have, as I say, a standard start-stop circuit, and I've also included this bit from my safe data, my fail-safe data block. That's sort of a summary of all my safety functions. They are all in the run state, which allows me to start. So if I get a safety error or a safety off command, I'm going to stop my start command, because I may use this other places throughout my program. And then it's only 2 lines here, and then my second network, I call my HMI routine. Well, let's go back to because what I want to show you next is what's included in this safe data block. Just a few commands I'm going to use. OK, and I'm going to request acknowledgement for my couple of my fail-safe functions that we'll get to in a minute. And there's also an error command that's used in the feedback function block that I may use in my standard program. The point of a fail-safe data block is that the bits within it can be both read and written within a safety program and only read within a standard program. That's the functionality there. So it's a good way to create this at the start of your program, should you want to transmit data from the safety program to the standard program. Again, this is one of those things, there are other ways to do this, but until you're more conversant and have maybe tested your own procedure for doing that, I suggest that you use these fail-safe data blocks. Next, we'll look at OB35, the cyclic interrupt, where we're calling our fail-safe program. And here I also said that we need to transmit some status bits from the standard program to the fail-safe program. In this particular small example, this is not a particularly big issue for a couple of reasons. There's a single cyclic interrupt block in this program, OB35. OB35 cannot be interrupted in this program by any other block, but it's possible in a complex system where the safety program could be interrupted by other organizational blocks that could change the status of standard bits that you use in the safety program, and then return to the safety to continue the execution of the safety program. The safety program is configured that it needs to see a consistent standard bits into it at the beginning and at the end. That's kind of a long way around the barn, but what it means is you should, in a complex system, you should get in the habit of writing your standard bits that you want to use in the safety program to another address. In this case, I've written the start command at 0.0 to 10.0, and I'll use it 10.0 within the safety program. This will ensure that the entire execution of the safety program executes against a consistent value for the standard bits. And again, same ways with my EDM circuit. I've assigned a bit for it to be to use within the failsafe program. These bits, these standard bits that you transmit to the safety program, can only be read. You're not allowed to write them in the safety program. The program is aware of where they came from, so it'll only allow you to read them. So that's what we've done. I'm going to use these two bits within my safety program. So I've written them to alternate addresses for use within the safety program. And then, just an example to show this point, I don't use these bits within my safety program, but had I configured a clock timing byte and used any clocking bits in the standard program, and then maybe I wanted to use those same bits in the safety program, you definitely need to write these. If you do this, if you use these, in this case the byte 90 timing bits directly in the safety program, you'll fault the processor in a couple of minutes at the latest. But so this is an example. Now I could use clocking bits within my safety program from memory byte 100. The only warning there is there's a execution call time specified for OB35, which in effect sets the minimum clocking rate for the safety program. So if I used a very fast clocking bit in a safety program that's called every, for instance, 100 milliseconds, and I use a timing bit that's supposed to execute maybe every 10, the safety program may always see it on or never see it on, but it most definitely won't clock reliably. And then here in the last run here is I actually go to my FB1, which is the block that contains my failsafe code. So we'll look at that here. I execute first off in there, and somewhere within that safety program I'm going to run my reintegration routine, which is how, if I were to get a hardware failure on any of the modules, this is how I would repair those modules and reintegrate them, activate them again within the program. Let's look at that, because that has some specific functions in it that should be done pretty standardly. This first line, if you've been in safety programs, this is this VKE1 bit in this FGlobeDB data block is a failsafe always on. So what I've done is I've just said that both of my failsafe input modules will require acknowledgement if they get passivated, if they see a hardware fault. And then all I do is, if any of them requires an acknowledgement, which means that they faulted, I repaired the fault, put them back in there. They're ready to go again, but I'm going to turn on my blue light to tell me that I need to acknowledge that they are ready to go again. And then there's a command that I push my blue button, I'm going to acknowledge all of the fail-safe modules in the project. That's what this block does. So that covers all the acknowledgement for all the hardware. And we'll see later when we get into the software how those are done. Let's go back to the safety program here. So that's a reintegration routine in a nutshell. So now we get into the actual code that I've written for my gate switches and my output module. In the configuration, we've chosen for the gate switches 2 normally closed contacts that are driven open. Think of them, they operate essentially as an e-stop, normally closed contacts that I open. So I'm using an e-stop block. I'm using the lower numbered address for one of those channels as my input to it, and because that device has been configured as a 1 out of 2 in the hardware configuration, program knows where the other half of that signal is. Again, I'm using my fail-safe always on to say that I need to acknowledge this block should it go off all the time. And again, I'm using that same blue push button as my acknowledgement. This block is capable of a instantaneous output, Q, and a time delayed off output, the Q delay. That's the off delay is set by the value set in this time delay variable. I've chosen to not use the off delayed version, only the instantaneous off. So I just put a value there, but I don't use any Q delay. I'm using as the output of this block the run state of the gate switches. I'm using a local variable because I've determined that I can do all my safety coding for these contactors within this program. I don't have a configuration where I need to take this value outside of this particular function block. Again, I'm using an item in the fail-safe data block as my acknowledgement request to illuminate the blue light should this block need to be acknowledged. And here I'm taking the diagnostics. There's a byte assigned to each one of these function blocks that'll contain various specific diagnostic messages. If you want to use them, you can assign a byte here where they can be accessed. This diagnostic byte can only be accessed in the standard program, not in the safety program. But that's we'll get to that later. What those bits mean. It's different for each function block, but this will give you more diagnostic information should there be a fault on this function block. On the next rung is my feedback block, which is where I'm doing my EDM monitoring. And you see what it's going to do is if I get a 1 on the on command, in this case the start command on, it's going to turn on the output Q, my 2 contactors. What the requirement to start first is I have no error, and I'm actually recording my error again in the safe data block because I may want to display that somewhere on an HMI. And what it needs to see is the inverse state between the feedback input, in this case, which is the status of the normally closed contact string, and the Q output. Q's on, this feedback better be off, and there's a discrepancy. There's a feedback timer that you set down here that'll define that state. So even if the Q is on and the contactors are closed, should you somehow get a short or a closure on the feedback terminal, this feedback block will turn the Q off and declare an error. So it's monitoring all the time. This Q bad IFO is is the there's a QBAD. There are bits associated with the status of channels and the failsafe within the failsafe modules that will allow you to determine which channel went bad. This feedback block uses it to, should the module fail, you're not going to need an acknowledgement of this particular function block. That's all that's doing there. And again, I've given it the failsafe 1 to always require an acknowledgement on if I should get an error in this function block. Again, it has a diagnostic byte that I've chosen to take out, and I'm going to show you in a minute how we're going to view those bits. So that's really simply how the feedback works, is that this function block is constantly checking for the inverse state between the feedback input and the Q output. And as long as that's true, it's going to keep the Q on or off based on the on signal. And here you just saw that what I did is, remember I had that contact in the start command rung in OB1. I've just collected the status of my 2 blocks here and just summarized it, so I only had to bring one contact out to the standard module. So let's look at, let me go back to, let's see here. So what I've done here is I'm saying, you see this first move, this first rung in my HMI. This is a standard function block. I'm gonna move that diagnostic data from the gate switch function block into a DB that I'm using for my HMI signals. This first one I've moved to byte 0. And then again, the diagnostic block, the diagnostic byte for the feedback block, I've moved to byte 2. Now, if you look at what that means and why I did all that, is here's my data block where I've moved them to. I've created a UDT for each one of those, and if I open that up, I see, because really what I want to get from my messages is I want to get on the bits that are contained within that byte without having to go back to the manual and see what each one of those bits represents. So that's what I've done there. So you may want to do that. Information for these various bits is also available in the online help. If you just want to see if you see an error and you don't want to display these messages, you can do it. You can do it just by going to the online help and seeing what each bit does for you. Let me close this back. So that's sort of a fast and quick look through the PLC program and the hardware configuration for this setup. What you see on this screen here is what I've shown here is shown in the classic version of the Step 7, and on the support site, this address here, this functional example 21331098 is another reference where you can see it done a little bit differently. And then also on this support site, if you search for S7F COTIB spreadsheet, you'll see that spreadsheet that you'll want to fill out whenever you start any of your safety programming projects. That was kind of a quick run through there. If you have any questions, you can reach me here at this address or call our 800 number and get a hold of me. But that's what I have right now. So let me, if there aren't any questions, that's the end of today's webinar. I'll get back to my my meeting organizer here to see if any questions have been put in. And with that, I thank you for listening, and I will see you next time.